not sure about me knowing my stuff, but we'll figure that out pretty soon. This is an awesome community, but this is an awesome space. I absolutely love this. Now, let's plug this in and see if the demo gods are with us, and then we can kick things off. Does it work? Wait, what? How does this thing happen? Okay. No. How does that? Entire screen, start mirroring. Is it like that? Okay, sick. There we go. So I usually bring a rubber duck, because like, at least in, I mean, rubber ducks are nice, and it's also that like, nobody pays attention in larger rooms when you go to conferences, like everyone's just speaking between each other, and usually like, sometimes I'll give a talk in a room of like 10 people, or it's 1,000 people. So like the ducky, I just put it to the mic, everyone gets a screech in their ears, and they know to listen. And then yeah, if there's no other reason to listen to me, it's either for the rubber ducky or not. But yeah, I want to touch a little bit on community, because like I started all my conferencing journey with community stuff. And the amount of energy that goes into producing even the smallest to the largest events, I'm sure you put like at least 20 hours of effort into every single event. The amount of, at least, maybe more than that. The graphic design, the writing of the descriptions, the planning, the coordinating with speakers, the amount of care that goes into it, it's no easy thing to build a community like this. And so I just want to say you've done a fantastic job, and I'm glad that we can be brother or sister meetups across different areas in Europe. But I'm going to be talking to you a little bit about something that I actually worked on a couple of years ago at a company called Navro, where Anna and myself actually met and worked together. And it's a story that's evolved a little bit. Now, you don't have to take notes if you were planning to do so. This is actually something called a Plod device that I'm wearing. It is a mic and AI recorder, which means that everything I'm going to do is going to be transcribed and turned into mind maps that you can explore afterwards. So anything that I talk about in my talks, you can always explore them afterwards. You can actually have an AI assistant that takes the context of the entire conversation, and you can actually dig into what was talked about, learned, because every single talk is unique. So when we're talking about caching, payloads, and other dark arts, how do we optimize user experience in suboptimal conditions? Now, this can be a very intense talk in terms of technical depth, so I'm just going to quickly gauge with the room. Who here is familiar with JavaScript? Who here is familiar with JavaScript? Okay, more than 2 years? Okay, who here works with React? Next.js? Unfortunately, well, that's a separate conversation. Any Angular devs here? Good luck. Vue? Okay, cool. Astro, Quick? Okay, respect, man. I'm gonna let the team know that. Cool. So the way I like to start this talk is by saying that Amazon did a study in 2006 where if you increased the amount of loading time for your web page by 100 milliseconds, you lose around about 1% in sales conversion. Back in the day, for Amazon, that meant 107 million. Today, that means a little bit closer to 3.8 billion. And now we don't have to optimize everything for the milliseconds. I'm going to explain a little bit of a story on how we can be pragmatic around the entire thing. Now, I already got a fantastic introduction. So yes, I am a staff software engineer, small PDF. The worst part about working at a PDF company is a lot of people ask me PDF questions. I don't know anything about PDFs. It's been a year and a half that I've been working there, and I've been asked the weirdest PDF questions. I work on the monetization. I am the monetization team, so I just know how to monetize PDFs. I don't know how to do anything with PDFs. Yeah, worked across connected TV, fintech, fitness stuff. I love web performance and engineering leadership. Anyone use Raycast before? Oh, come on. Raycast currently used it before? You gotta use it. It's incredible. And like now there's no excuse if you're on a Windows machine because they support Windows, they support iOS. I don't know why they support iOS, but they do. And you can build some really cool extensions on it, and I like contributing to it. And then yeah, Zurich.js is a thing. So to set the stage, I like to show this photo because I'm also from not just Switzerland, I'm also from Pakistan. And over there, traffic looks a little bit like this. And generally, you're driving a lot of Japanese cars over there. There are a lot of potholes, unmaintained roads, floods. Not like the roads probably in Germany and Switzerland. And most of these Japanese cars that are driven over there, they're very cheap cars. They're made for the mass market. They're your Hondas, your Toyotas, all that sort of stuff. And some of them can actually last all the way to 620,000 miles. I gave this presentation in America. That's why it says miles. Otherwise, it would have been kilometers. I was trying to be regionally friendly. And what's incredible about that is in Pakistan, they most likely don't even have the money to service them frequently. They're going to miss the service intervals. You're running the tire tread down all the way till it's bald or popped. And so you're using these vehicles in conditions that they weren't designed in. They were designed in a factory. Now, if you do that with a German car, and they're great, they go on the Autobahn, they have to take exactly a certain level of octane of fuel. They have to have a maintenance interval every 6 months, otherwise they go kaput, exploding, you have a $100,000 bill on you. Now, I like to think of this also the same comparison between localhost and the real world. We develop in these perfect little boxes, our homes, and they've got great Wi-Fi connections. Either you're connected directly with Ethernet connection, and you're on M1 Max maybe, or you're on M4 Max, and you've got all the power in the world. Much, much more than you need for most web apps, but probably just about enough for all your Chrome tabs. So in localhost, you can deal with all that stable network, great bandwidth. You're a single user in an ideal environment. And in the real world, it's very much the opposite at times. You have high latency, unreliable networks, mixed devices and throttle CPUs. In the heat in the summer in certain countries, your CPUs are going to be throttled because they can't even deal with the temperature and the cooling. So there's a lot of problems there. It's not even just the CPUs at base temperatures. And then you have to deal with weird states across multiple deploys, like partial caches, stale data, and flaky APIs. And so, like, what's the problem statement? And we talked a little bit about it before. And the problem statement is, what challenges do developers face in creating a seamless user experience due to complex data fetching, specifically? That's something we very frequently do as web developers, and the management of that data. Or more so, how can we build these optimal solutions in these suboptimal environments? Why bother? Now, 0 to 2 seconds is that ideal window for rendering something, but we can't render everything in 0 seconds. So how do we understand the scope of this a little bit more? And I like to look at response times and the 3 important limits of those response times, as you know, as an excerpt from this chapter called usability engineering. So really good read. And so if you look at 0.1 seconds, this interaction, an interaction that loads in around about 0.1 seconds, the user feels like the system is reacting instantaneously. And so when you move that all the way to 1 second, you start to get to the limit of a user's flow of thought. So if you're going through a workflow, you're going through a Google Docs, you're writing a bunch of things, you're going and you're clicking multiple functions on a web application, if any of those things take longer than a second to load, while at 0.1 seconds it feels instantaneous, longer than 1 second, you interrupt your flow of thought. Have you ever had that moment where you're typing something into a search bar and then all of a sudden it slows down and you don't know what you're typing anymore because you're losing your words, and like you want to stay within a user's flow of thought. And then if you get all the way to 10 seconds, it's the limit for keeping the user's attention. And back in when all this stuff was written, 10 seconds stands. I think in the age where you've got all your TikToks and your doom scrolling and your Instagrams, 10 seconds is not going to hold. Has anybody actually waited 10 seconds for a website to load? Okay, you have the patience of a saint. I can't bear it. I'll give them 4 seconds and I'm out. But just to get a little bit of a comparison in terms of bounce rates for somebody going to the website and then coming off of it, the 1 to 3 second mark, it's around about 32%. If you move that all the way up to 10 seconds, you're looking at 123% of a bounce rate. So it's a very significant increase. And that may not have to be for all of your pages. You have low traffic pages that you don't care to have so much conversion for, but for your high traffic pages, this can make a massive difference. So the technologies we're going to be talking about today is Next.js. React is the library, Next.js is the framework. And you can ask me all about opinions on the framework afterwards. And then TanStack Query. Has anybody used TanStack Query before? It is absolutely incredible, and they just released TanStack AI a couple of weeks ago, but who isn't releasing an AI thing? Yeah, and I wasn't allowed to say that. Sorry, I'm just getting the water. I wasn't allowed to say it for because I met Tanner last month, and he told me about it, and all I was allowed to say publicly is that it was pink, because they choose different colors for every single package. So it's interesting. So when they decolorize something, it means that they're preparing, I think, for for a new release of something on the hood. And it's, the Tanstack team is absolutely incredible. But it started all with query and originally was called React Query. And it's a powerful, if you look on the website, a powerful asynchronous state management library. And it often is confused with just being a data fetching library. It is not your Axios or whatever else it is. It is a state management library that so happens to be incredibly good at asynchronous work, which is predominantly your data fetching. So when we're talking about data fetching, we're talking about APIs that we work with, and I like to differentiate in a couple of API types. First, I like to differentiate in one type of API, which is public APIs. You've got public APIs like your Star Wars API, your Pokemon API, APIs that exist out there in the world. If you go search, free public APIs, these are APIs you did not build, that you are not paying for, that you have zero control over, and you have no idea how they operate, what infrastructure they operate with, what kind of versioning they do. So they more often than not, they're black boxes. You have no control over them, and they're subject to breaking changes. You cannot reliably assume that they abide by semantic versioning or anything of the sort. Yeah, there's a slide on that. Then there are internal APIs. So if you work in a product company, you'll either be working across functional teams or you'll be working with separate backend and front-end teams, where for a front-end UI, you will be developing a bespoke backend system that operates to serve that front-end and no third-party users, no external consumers, which means that tomorrow, if I want a specific API, I can just go ask my backend team and they'll build it for me. So you can freestyle the API. You don't have to abide by any REST design principles. You can just do whatever you want. By REST design principles, your GET requests are normally meant to be idempotent. I've known internal companies that build internal APIs that have GET requests that just mutate stuff for the fun of it. And that's just because they can and they have no external dependence. And they may even be lacking authentication for the most part. So you don't have to worry about a lot of things there. Then there are partner and product APIs, which we're going to be focusing a little bit more before, which is an API that is sold as a product for third-party consumers and designed as such. And so when I was working at this company called Navro, what we were doing is we were designing a financial dashboard, but we were consuming an API that was also be designed as an API-first product that was sold also for machine-to-machine communication. So what we had to do is we had to make use of the APIs for no matter in what state they were given to us, and we could not request bespoke endpoints for things that we wanted to do in the front end. So that gave us a couple of complexities to work with, and you have to abide by things like deprecation policies. So you can't just adjust things. You maybe have to wait a 6-month period for something to be deprecated, then to be adjusted to the new API structure, and so on and so forth. They have to abide by semantic versioning for the most part, especially if you're dealing with financial regulation. And then you have to also optimize for widespread compatibility over internal optimization. Now, let's take a second and put our technical lead hats on, or your PM hats on, or whatever you want, because we're going to act like we got a Jira ticket. Let's not complain that we're using Jira. We could use Linear, we could use Notion, but today we're using Jira. It's okay. And let's say our front-end team needs to design a dashboard chart that displays the distribution of birthdays for the top 5,000 users in the system. So the data is available via an API endpoint, which returns a list of users with all that data. And so important information is always going to be highlighted in yellow. The backend is unable to provide a new endpoint or a data warehouse, which would have been ideal in this scenario, that returns the required data format. And there's a limit of 1,000 users returned for every single request. So if we're thinking about this, and before you look at the diagram, if you're thinking about this, I've got 5,000 users worth of data to show, and I've got an API that can only return me 1,000 at a time. So I've got to start thinking about, I need to request this API multiple times to get all the information I need to display my chart data. So if we look over here, and I'm going to be moving a little bit, but I'll stand still now. We're going to look at this diagram and start our architectural journey over here at the user interface. I know it's a little bit hard to read. What we would do logically is we have to make 5 requests, so we're going to make those requests in parallel. Maybe I can move the TV ever so slightly. There we go. We can make those requests in parallel. So we're doing those requests on the client side. 5 of them shot off at the same time. We're not going to do them sequentially. Parallel is more optimal. When you're loading something, or when you're fetching any data, you're going to normally have a loading state. So you're going to show something to tell the user that you're doing some work in the background and fetching some data. And you have 2 things that can happen. You have an unhappy path and a happy path. If you have an unhappy path and something goes wrong in that process, what you'll generally do is you might persist the loading state because you're going to go and retry. Something went wrong the first time, I'll retry again, especially if it was a 500. You have no idea what the error was. Dependent. Generally, you wouldn't do that for a 400. Then you may have some custom logic to manage that retry and decide you'll either to retry all of them or you'll retry just the ones that failed. There's some complexity to decide which kind of mechanism you want to do to recover from this failed scenario. You could then have the happy path, where then you get the data back, you map it, so you're going to transform it in a structure that you like, that you want to work with. You're going to set it into state. You're going to render the initial UI. And then let's say you touch another piece of the UI and you've suboptimally handled your state. Normally, you'll do a lot of data fetching initially without any third-party library using a use effect. Whole other escape hatch issue over there. And if you do a React state change to something irrelevant to that chart data, what might happen is you re-trigger the use effect because one of the dependencies changed, and then you go make those 5 requests again. Another change happened, make the 5 requests again, and then you may land yourself into a place where if you have a rate-limited API, you get a 429 error, which means you have too many requests happening. And so if you were to look in terms of code of how an initial version of this architecture or this code looks like to be able to fetch these 5 requests, what we would create is a use fetch data hook. Over there, inside you're going to get fake data. Over here we're getting a faker API to give us the user data. And we're going to essentially pass a quantity of 5 to be able to make 5 parallel requests. We get the data back, the promise resolves. We're going to get the birthdays by month in that response. We're going to map it to this structure, and then we're going to pass it to map chart data, which is going to then map it to what we're going to pass to our chart. And by passing it to our chart, we're going to set that data into state, and then that state is passed on as props to the chart. That's a type of function that you very commonly see in a lot of code bases. Should we look at a demo? Initial architecture. So I'm going to play this, and we're going to be loading the page initially and waiting for all 5 requests to resolve. Just wait a little longer. Whew. It's a long time. Did you last the whole 13 seconds? And if we go and dig inside there, you'll see that we have information like their date of birth, ID, location, login, and just things you probably just don't want to deal with at all. You even have their password in there in that request. It's absolutely ridiculous. But it just seems like to render the data on that chart, we're receiving a lot more information than we want. And let's say I don't want light mode and I want dark mode. Now I found myself in a place where I made all those requests again. And light mode and dark mode, something that all our websites want, maybe an inadvertent change that you've made, you've put that into a context API, and then the entire tree is re-rendered. And then you're making all those requests all over again. Cool. If you were really good at math, which I am not, you will have calculated that the entirety of that payload of those 5 requests was 1.5 megabytes of payload. And around about 80% of that data is unused data. I'm reminding myself I shouldn't move as much. And if we look at the key factors of this initial implementation, we have custom retry function, which if we write this ourselves, needs testing, maintenance, and it's subject to bugs. There's no caching by default, so it's not great. The state is really complex to manage globally and handle the staleness of the data. And then you have to map the data on the client, and that means you'll maybe be slapping on one of those use callbacks and use memos to make sure that when re-renders happen and so on and so forth, you're not recalculating the demo, recalculating all the map data and then passing it to the charts. Then you end up having a place where you're doing this additional effort to make sure you're still performant. And then, of course, we've not optimized this payload for state and for caching. Has anyone ever heard of the 14 kilobyte rule? I'm so impressed. Usually nobody hears about it. So the 14 kilobyte rule, and this was advice more from multiple years ago. It was predominantly a rule around the initial congestion window for network requests. So 14 kilobytes fits within a single initial congestion window, and it minimizes something called round trips. And we'll look a little bit about what that means. So when you're loading a website, and let's say you're loading a 14 kilobyte website, that's what the initial HTML looks like. You go on a particular URL, say, can I see the website? I'm going to go to the server. It's going to say, give me the information to be able to load this website. All 14 kilobytes come back. Super happy. If it's 15 kilobytes, it's going to say, can I see the website? Here's the first 14 kilobytes. Then it goes, takes a round trip to the server. It goes back, and it's like, hey, can I please see the rest? This is the initial window for the data coming back to load the website. And you get the final kilobyte, and then you're all good. And so what's really interesting is that between 14 and 15 kilobytes, you can see around about a 600 millisecond delay in loading time of a website. But just going from 15 to 16 kilobytes, it's just a couple of milliseconds, under 10. It's a very marginal difference. So fitting within the initial congestion window of your network request is incredibly important. Now, this really doesn't apply as much anymore these days. This was something really back in the day was a bit more important, but the principle is very relevant. And with most modern CDNs like your Cloudflare and so on and so forth, 46 kilobytes is more likely what the initial congestion window is. But this needs to be individually tested for every single either CDN that you're working with or wherever you're hosting your servers. It's not one fixed number, but the concept is about the initial congestion window. And when you're talking about this ICW, you have to also think about the stall. And the stall is a little bit that story about the round trip. And so the stall cost is the cost of a singular round trip to a server. So the round trip to the server depends on the type of user making the request. So on a LAN connection, connected Ethernet cable, so on and so forth, it's 1 to 5 milliseconds. So I get the 14 kilobytes, go back to the server. That time to go back to the server only took me 5 milliseconds. I get the rest of the 1 kilobyte. Barely noticeable. Typical broadband is 30 to 70 milliseconds. Still pretty decent, but when you find yourself in 4G, 5G networks, you can see yourself going up all the way to 200 milliseconds, and it gets a lot worse when you go all the way down to 3G, which if you're talking about emerging markets, that's going to be very common. And so the general concept is get your critical rendering payload, and whatever that may be, under the initial congestion window. And this is where I like to introduce a little bit of a concept called backend for frontend. Has anybody ever heard of BFF pattern before? It's not something new, again, but we're going to be employing it here to have an interesting outcome. And the pattern specifically, there's a website called BFF Patterns out there that has multiple different ways that you can employ the BFF strategy. We're going to be using something called a transformation bridge or an aggregation proxy pattern specifically. And the idea of that is a little bit in the name. You're going to be aggregating a bunch of data via this proxy, this thing that sits in the middle, and sending it to a client. And the beauty of this is you can have it adaptable for platform requirements. So let's say you have multiple clients. You have a web client, a mobile client, and a TV client. You can have a singular proxy serve all of those 3 clients. You can decouple the concerns over there. So all of the effort when it comes to data transformations, mapping, even unit testing, all that stuff, it sits in its own place because you only care about getting chart data and having it returned. And you can optimize that singular part just for performance. So whatever data structure you want to use, whatever algorithm, however you want to manage the mapping, whatever, you can handle that happen in that single proxy. So an ideal payload, actually, if we wanted to render that chart, looks like this. We just want a bunch of buckets for their birthdays. Tell me for January the count of the amount of people, and at the end give me the amount of users. It's a much lighter payload than what we had to do before. And let's say we're starting with this all over again, the same architecture, but we're evolving it a little bit to having one API request now to the Next.js API handler. So Next.js, you can create those API routes. You can do this now in multiple frameworks. These are full stack frameworks, and you don't have to be tied to the full stack frameworks. You can actually have these proxies set up as your Node.js microservice or a Golang microservice. You're not tied. This is an entirely framework or language agnostic principle. Make that one request, you're sitting yourself back into a loading state, and then you're still making those 5 parallel API requests, but those are happening now server side. The unhappy path is exactly the same, where if you're unhappy, you fail and return an error code, and you have to just pass along the retry management down the line. The happy path, you map the data on the server, so now that effort is done on the client, you save yourself all your use memos and use callbacks, which you should probably most likely never use unless you're using context APIs. Send the data to the client, set the state, render the UI, but you've not changed the way we manage states. That means if you do something suboptimal in terms of your state management, you risk again your 429s. And so if we evolve this a little bit in that hook that we initially created, what does this look like? So we're now moving it to this use fetch data hook, which is just making a singular request to that proxy, and we're getting back the payload. We don't think about anything else. No other effort. The front end doesn't have to care about how the data is being dealt with. It just needs to care about getting the data, setting it in state, dealing with it afterwards. And before I move forward, where this gets really interesting is we're going to be at the caching point later on, because if you generally cache via local storage also has limits to it, around 3 to 5 megabytes depending on your browser. So if you were dealing with a 1.58 megabyte payload initially, and that's not the only network request you're making on your client side, you're also dealing with a lot of other data, you can see yourself running out of local storage and caching space pretty quickly. So that's also a level of optimization you're doing there. So what are the key factors over here? We've done some failure isolation. So we're isolating all the failures to happen at the proxy level. The proxy level has to deal with this. Then we're having a clear separation of concerns with our code-based management. We're mapping the data at the proxy level, and then the payload is optimized to, just like a minimum viable product, the minimum viable values you need for your chart. Let's look at demo 2 and just see how moving this to a proxy and doing nothing else changes the outcome. You want to see it? Yeah, we need the energy of 100 people. There were 100 people last time. We're gonna have the energy of 100 people. Cool. So we're making one singular request to this birthdays API, and let's see how long it takes. 5 seconds, over 13. All we did was move it. We did nothing special. I'm not giving you any algorithm, any caching. There's no memoization. There's nothing else being done. It is just taken one place, copied, and pasted somewhere else in the same code base. But as you saw, we will probably have that same bug where if you're switching between light mode and dark mode, you're going to be re-requesting those birthdays from the API. And we've now shoved all of that into a 300-byte payload. That is a massive difference. Now, if we look at a network bandwidth level for what a 1.58 megabyte payload would load under, for Wi-Fi, it's 340 milliseconds. Again, this is very dependent on certain key factors, but around about 340. 4G, 700 milliseconds. We're about to hit that place where we limit flow of thought. 3G, 6.5. Very complicated to deal with and optimize that at a UX from a UX perspective. If we're talking about 300 bytes, 200 to 210 milliseconds, 200 to 210 milliseconds, 200 to 210 milliseconds. Because your problem there is not actually loading the payload. Your problem there is actually just your initial round trip to the server. And you don't have to do any subsequent round trips. And that's where the cost was, beyond the fact that the payload is very large. That's where then the topic of ingress and egress comes up. Has anyone heard of ingress and egress before? This is more of a DevOps, well, you of course have. This is more of a DevOps or architectural or SRE type concept, but ingress is the data coming into a network, and egress is the data coming out of a system or network. And generally, cloud providers won't charge you for ingress. They're very happy for data to come into the network. They're going to charge you the second the data wants to come out. And so if you're thinking about an infrastructure cost perspective, the BFF pattern is actually not that bad because the ingress is where the larger payload is. At the egress level, you're actually compressing everything. You don't have to deal with as much data coming out. So from a cost perspective, it's not too bad. And then there's also hand in hand the topic of FAAS or IaaS. Anybody want to give a guess what on earth those mean before we dive into it? It's beautifully said. There we go. Yeah, it is function as a service and it's infrastructure as a service. So like, those are the two main ways you really deploy something. And your Next.js API handlers are going to be your edge functions, but if you're dealing with a Node.js microservice, that's going to be something that's going to be deployed separately. But if we're talking about function as a service initially, and you're talking about initial average ingress bandwidth, which is very hard to calculate, you're talking about 1 to 5 gigabytes of ingress bandwidth, which means that the network is going to be very stable at the proxy level, but your variant network bandwidth is going to be at the client level. And so that means you want the highest network where you're doing the majority of the requests. So that's your AWS Lambda, your Vercel edge functions, your Cloudflare workers. Your biggest compromise when it comes to edge functions is the fact that you have cold start times to think about. So you have 100 milliseconds to 2 seconds when it comes to cold starts. That's going to impact performance. But once they stay hot, then they're hot for 5 to 60 minutes. So a lot of your free tier Netlify and Vercel websites, you'll see if you're not paying for anything, after you've not looked at the website for a while, you'll see that the initial time it loads takes a very long time. That's your cold start time. What some people do as tricks is that they actually, I don't know, what I did was I put a Raspberry Pi with a little ping that sends to the website every 5 minutes to keep the server hot. And then you can use a free tier with instant loading time, but like stuff like that. And then we're talking about the infrastructure as a service level, much higher bandwidth, higher cost too. And that's your AWS EC2, your GCP compute, so on and so forth. And that's going to be if you're doing this as a single Node.js microservice, but it's always running and there are no cold starts to deal with. And so now we're going to bring TownStack Query into this conversation. And don't worry, I'm only through 98 slides of 130, so we're going to be there very soon. Cool. So I'm not going to tell you everything about TanStack Query. The documentation itself is absolutely fantastic, and even TK Dodo's blog is great for a lot of the resources. But it's got a lot of jam-packed features to be able to help you with all of your asynchronous state management. And so now this is going to be a little bit harder to read, but we have evolved our architecture to plug TanStack Query into it. And what does this mean? We started our user interface. At the client side, we're doing the same thing we did before, which is we're making an API request to a Next.js handler. But now React Query is dealing with this for us. We're passing this to the use query hook, and we don't have to do that thing where if we had a use effect, then you, at the beginning of the use effect, you do set is loading true, then you make the network request, then you do set is loading false, then you do, I don't know, try catch, finally, whatever it is. It's a lot to deal with even just loading states. You just delegate that off to TanStack Query, it's going to deal with it. Makes the 5 requests, unhappy path, fails and returns to the client. React Query will handle standard retries or even exponential backoff-based retries. Does everybody know what exponential backoff-based retries are? So exponential backoff-based retries is, a normal retry is I'm going to try 1, 2, 3 times till I get a right response. Exponential backoff is once, wait 1 second, twice, wait 2 seconds. I'm backing off each time. It's like if somebody's really irritated with you, you touch the API, you back off. You're a little scared, you're a little worried, they're a little bit temperamental. You give them some time to breathe, go back to them again, and then you can add also jitters in terms of the timing of those API requests, which then solves thundering herd problems, which is something I'm not going to get into right now. So yeah, it handles that for you, the retries. Then you go to the happy path, map the data on the server side, same as before. Send the data to the client, and it's going to cache it for you. It's going to start with in-memory caching, but then you can plug in a third-party library to be able to do offline caching. Generally, you use something called local forage, not local storage, but local forage is a very interesting solution because what it does is, depending on the browser compatibility, it will decide dynamically whether to use WebSQL, IndexedDB, or local storage. So whatever's the right option depending on the browser, with the same API and interface that local storage has. React Query derives the state from the response. We render the UI, and let's say we messed up the React state change again. What's going to happen is React Query is going to first say, hey, is there a cache? It's going to check the cache. It's going to be like, hey, do I already have this data? Is it not stale? I got a cache hit, render the UI. So even if you suboptimally designed your state, React Query will sort of help you out over there and catch you and make sure that you're not going to trigger re-renders again when you have data that is fresh. Of course, if it's stale and it misses, you're going to go all the way back to the start of the journey, make that 1 request, then makes the upstream 5 requests. And if we see how this looks a little bit in an evolved code base, you are passing that same proxy fetch function to the use query. You're passing now query keys, which are going to be hashed, and that's how it's going to know what to access in terms of data. And what is really nice with this is the fact that as query parameters evolve over time, and if you have dynamic query parameters, you'll have separate cache stores created for every single piece of data. Something very hard to design for yourself. And so what we've done now here is we've delegated a lot of stuff to a third-party library. And that's not the hardest thing to do. We delegate a lot of things to third-party libraries these days. Controls the error handling, the deriving of the response states, caching. It's optimized for the caching. The optimized payload can be cached with multiple different strategies. Re-renders are limited. We have resilience out of the box. So it's very configurable to have the retries in the back off. And we can just go one step further in this. We can even shave more off than the 5 seconds. So if we start our journey on the server instead of the client, so now initially we've been making our requests on the client side, what we can do is we can do a prefetch. And so if you're dealing with Pages Router, Next.js, App Router is a little bit of a different story. What you can do is with TanStack queries, you can say, hey, when you're on the server, before you generate the initial HTML, I want you to fetch some information and populate or dehydrate this cache. You pass it over to the client when the hydration process takes place. Are we all familiar with what hydration is? Okay, cool. When the hydration process takes place, it's going to go and derive the initial cache from what was passed from the server, which means that no network requests are made on the client side. This means that you will have instantaneously a page with information and no loading states, and we'll see that in a demo. So we're making this request on the server, one API request that makes the 5 requests. We're going to have a timeout controller here, because what happens is that if a request takes too long on the server, if it takes longer than 5 seconds, you have a blank browser. nothing is sent. Whereas on the client side, you have your root HTML generally sent if you're dealing with a SPA or a React type app, but different in XJS. And what happens is that you at least see some initial HTML, you start a loading state, and then you continue to fetch the rest of the data there. On the server, you haven't populated the initial HTML, so you have nothing to send. You're blocking with this. So you have your loading state. So if the timeout passes 1,000 milliseconds, cancel the request and start to recover on the client side. We do the loading. We have the unhappy path. It fails. It retries on the server or retries on the client, so on and so forth. If we have the happy path, as we discussed, we set the cache on the server. We dehydrate it. Then we hydrate the client. React Query derives it on the initial render, and we have the same story as we did before. And so we won't get into the topic of optional and critical queries, which is something that I also tend to go into in the is an hour-and-a-half version of this, and I even do an 8-hour workshop. So trust me, this is the short version. We create that prefetch. We set, let's say, 2.5 seconds. Is that you have 2.5 seconds to make this work, otherwise bail, because then my user is not going to pay attention to my front end. Or let's say if we made it 1 second, you're saying that, hey, you're giving the time before flow of thought is interrupted. At that point, send something so they have something to look at and interact with, and then continue the flow of thought. Fetch the request, dehydrate it, pass it to the front end. Very typical story with Next.js. And so we've reduced UI delay over here, and we're sort of almost load balancing the data a little bit. So we're reducing the client data load, and we're doing some work on the server and some work on the client. And then we're also having data recovery strategies in here. So in optimal scenarios with optimal bandwidths, we're showing the best UI, the fastest UI possible, but when in suboptimal conditions, then we recover it on the client side. And we're gonna look at demo 3 that's gonna put this all together, and we're actually gonna start on the Zurich.js website. And why I'm doing this is because I wanna go to demo 3, and you're seeing something's happening on the server, nothing's being sent because we're fetching and no timeout has occurred. So it took a long time for that to initially render, but now the second it does, everything is there. Now, if I go to demo 4, where we've reduced the timeout, it's going to give me a second, and then it's going to bail, and it's going to have a loading state on the client. It's going to try to recover from that. And that's the difference between having blocking network requests on prefetching on the server and then having a recovery strategy on the client. And we talked a little bit about real-world results all the way at the start. So where on earth were these demos filmed? On the plane to New York. On the plane to New York to React Summit, all of them were filmed right over here on a network connection on the plane. 13 seconds was how long it took initially on the plane. I think if we look about this one, I have no idea how long the initial one takes, but I think it takes around about 3 to 4 seconds. So we shaved almost 10 seconds in an airplane. And that's a pretty bad network connection to deal with. And even you're talking about there's certain network packages on the airplanes where you have maybe a 25 megabyte limit on how much you're paying for. So yeah, actually we went to 3.8 seconds. So we dropped down by 10 seconds, and you're actually saving the data, and it's cheaper for you to have data on a plane because sometimes you have limited packages. You pay $30 maybe for 1 gigabyte of data or something like that. So those are the real world results, and these are the actual real network conditions on the airplane that I recorded to prove that everything was. So yeah, what was it? The ping was 927 milliseconds and 4.8 megabytes per second. Now, towards the end, Faris, instead of jumping through all the engineering hoops, couldn't you have just done the damn endpoint? It's not the point. The point is, sometimes you gotta be pragmatic, sometimes you gotta be curious, creative, and when I did have to implement this at that company, that solution held for 2 years because we could never prioritize building that stuff into the roadmap. And I don't even know, but it may even still exist till today. That's it.